Welcome to this fourth lecture in EE557. In the last lectures we have seen some probability review concepts, and in this fourth lecture we are going to finalize our probability review or reminder. So we're going to be looking at systems of this form. Xk plus 1 is equal to f of xk, wk, and yk is equal to, let us say, h of xk and vk. In this system there is no input. It is not important. The input usually does not change things much if it is not selected by feedback. So I remove the input terms from this system. And here I have some noise terms. Wk is the process noise and Vk is the measurement noise. In general, this system is stochastic, so there is nothing called knowing about the state. We will never know the state because measurements are usually have lower dimension than the state, and we only observe the measurements. So there is so knowing the states exactly is impossible. But the best thing that we can say, so suppose that we have observed the measurements from time 0 to k. This denotes y0, y1, going until yk. Suppose that we have observed these measurements. The best thing that you can do about knowing the state xk is to calculate the posterior distribution of the state given all of the measurements. Okay? So if you know this density function, the density function of xk, given all of the measurements, then you know the most about the states that you can. So and people always try to calculate this type of distributions. If the system is linear and Gaussian, if f and h are all linear in xk and wk and xk and vk, and if the noises are Gaussian, these are Gaussian distributed, and suppose that the noises are white as well, in that case this distribution becomes a Gaussian density, and this Gaussian density is usually denoted as xk given k and pk given k. So this is the posterior mean of the state. This is a posterior covariance. And then we can find a recursion for this x at k given k and pk given k. That recursion in the linear Gaussian case is called Kalman filter. So, but in the general case, if f and h are nonlinear and wk and vk are not Gaussian, in that case the only thing that we can do is to calculate this distribution, and that distribution in general will not be a Gaussian distribution. So it would be important how such a distribution evolves in time. So what do I mean? How actually I can start with this distribution. It's not a Gaussian anymore. So I have xk given y0k, and how I can advance the time one step, and how I can obtain pxk plus 1 given y0 k plus 1. Okay? This would be important to calculate this distribution recursively from one time step to the next time step. Okay? So in general, this requires to calculate this distribution from this distribution requires some rules in probability density functions. And usually we go from this density to this density in two steps. Okay? So one of the steps is this. The first step is to advance time, not the measurements, okay? So the first thing that we do is to calculate xk plus 1 given y0k. So when the measurements from time 0 to k are known, we calculate the density of the next state, okay? This step is called prediction update. So no measurement has come from here to here, but we advance the time from k to k plus 1. So this is therefore knowing the measurements until the k time step. I'm trying to predict the state at time k plus 1. Okay? This is why it's called a prediction update. And sometimes, because we advance time in the state from here to here, this is also sometimes called time update. Okay, but you see that this is not the same as the next distribution that we would like to obtain. So what we do is actually we first go from here to here, then we go to this distribution. So from here to here. So we obtain xk plus 1 given y0 k plus 1. So in this case, the state remains fixed, so it is xk plus 1 in both of the distributions, and we add one more measurement from here to here. Okay, so this is from this step to this step, I need to incorporate the effect of the k plus first measurement in this distribution. That is because a measurement is added in this step. This update is called measurement update. Sometimes this measurement is called to have a correction effect. So sometimes this is also called a correction. All right, but we obtain a recursion obtaining this posterior distribution from this one, and we do a single recursion, a single iteration in two steps: prediction update and the measurement update. And in the course, we are going to actually try to obtain some formulas connecting this distribution to this one and connecting this distribution to this one. All right, in order to be able to complete a single recursion. And obtaining such recursions will require some probability rules or some probability theory knowledge. The first thing that I will look at is I'm not going to cover this topic, of course. I'm just trying to motivate the tools that we are going to learn in this last lecture of the probability review. So in the prediction update, we are going to derive a formula in the following form: pxk plus 1 given y0k will be shown to be the following distribution. So I have integral xk plus 1 given xk, pxk given y0k dxk. Okay? So you see that this formula takes this distribution, and it obtains this distribution. Okay? So this formula is called Chapman-Kolmogorov formula. And we are going to derive this in the course, but in order to be able to derive such a formula, we are going to require a probability rule that you have learned in your probability courses before, and that is called the total probability theorem. Okay, so this Chapman-Kolmogorov formula is nothing but an application of the so-called total probability theorem. And in the second part, we have something called measurement update. And in that case, I need to write this distribution in terms of this one. So it is not also difficult once you know some probability theory. So it is given as follows: yk plus 1 given xk plus 1, p xk plus 1 given y0k divided by pyk plus 1 y0k. This is the measurement update formula, and it relates this predicted distribution with the updated distribution. This is the predicted distribution, and the updated distribution is given like this. And this distribution that we multiply, this is not a distribution actually. This is called the likelihood function. It is used in order to make the measurement update in the density domain. And the tool the probabilistic tool that is necessary to be able to derive such a formula is called the Bayes rule. So Bayes is a very important statistician, and almost all estimation theoretic methods are actually using the so-called Bayesian approach nowadays. So we are going to actually be able to derive such a formula using something called Bayes rule, and that is going to be a part of our probabilistic review in this lecture. And the final thing that we are going to cover in this lecture or I will remind you in this lecture, is going to be the transformation of random variables. So here we see that this noise is transformed with the function f into a state. Similarly, in the measurement noise is transformed into yk. So it is important for us to know what the effects of those transformations would be on the density functions. So suppose that wk is a Gaussian random variable, and suppose that xk is deterministic, it's fixed scalar. What would be the distribution of this f of xk, wk? What would be its density function? So we can ask such questions. So we know, for example, if f is linear and xk is Gaussian, wk is Gaussian, if these are jointly Gaussian, then xk plus 1 is going to be another Gaussian random variable or random vector. So in a similar way, we can ask the more general question: when the density functions of xk and wk are given, what would be the density function of xk plus 1? Of course, it's in general not possible to obtain the exact density function, but it would be still nice if we know some theory about how to derive such density functions once the density of the argument variables are given to us. So the first thing that we're going to see in this lecture is going to be total probability theorem. You might remember this from your probability classes in the past. So I'm going to be writing the random variable versions here. So I have a z1 variable, and suppose that I'm considering an event which is represented by the z1 being inside this set z1. And suppose that I'm considering a second random variable or vector, z2, and suppose that I'm considering the sure event, okay? Suppose that I'm considering the sure event where z2 is inside its own space. So this is an event with probability 1. So now I'm going to be writing the following decomposition of Rn2. Suppose that I decompose Rn2 into some subsets. Okay, so suppose that this is Z21, and I have here union Z22 going until Z2n. Okay, suppose that there are some subsets of Rn2, and these subsets, their union would give me Rn2. Okay. And suppose that these subsets are also mutually disjoint. Okay, so I'm assuming that Z2i intersection Z2j is equal to the empty set. Okay. So what does this give us? So then this is true when I is not equal to j, of course. Otherwise, the intersection would not be the empty set. So I have disjoint subsets here. And I know that these subsets would cover the whole state space, the whole space of the random vector Z2. Then when I look at these events, Z2 is inside Z2i, these events would be mutually exclusive. So that means that if Z2 is in one of these subsets, then it cannot be in any other subset. And Z2 should be in one of these subsets, because the overall space is Rn2, and these subsets would cover Rn2. And then I can write the following theorem. This is the total probability theorem, if you wish. So I can write this distribution. So I have Z, let me look at my notes here. So I have here, sorry. So I can write Z1 as follows. Okay? So this is, we know that we have defined such a distribution as follows. This is probability of Z1 being inside the subset capital Z1. Okay, and Z1 is a subset of Rn1. And the total probability theorem tells us the following expression. It tells us the following expression here. P Z1 is equal to, so I have a summation I from 1 to n over these subsets here, and I have a conditional probability distribution function Z1 given Z2, and I have here Z1 given Z2i, and I have another distribution, this time for random vector Z2, and I have Z2i. Okay? So that is the version of the total probability theorem for two random vectors. I express the probability distribution of one random variable in terms of the conditional distribution of the same random variable and the marginal distribution of the second random variable. Okay? So every probabilistic rule given like this has a counterpart in the density version. And in the density version we have let us write the density version. The total probability theorem has the following counterpart. P Z1 is equal to the integral P Z1 given Z2, and I have here Z1 given Z2, and P Z2 dZ2. Okay? And this integral is over the whole space of Rn2, space of the second random variable, random vector. So I will not be working on the distribution version here. It is not used commonly. At least we will not use it in this course, most probably. But the density version is important, and you would see that it is actually looking like this. When I try to express the distribution, so these conditionings really are not important here. We are going to give another density version with some conditionings here. But here the thing that you need to see here is that in order to be able to write the distribution of Z1, we added an additional random variable here, vector here, Z2, and then we have written this marginal distribution in terms of conditional distributions, etc. So it's actually looking like this one. In order to be able to write the density function of xk plus 1, we have actually added the additional variable xk here, and then we integrate it with respect to xk. So this Chapman-Kolmogorov formula would actually look like this total probability theorem, and it is actually how we can derive this Chapman-Kolmogorov formula once we see this type of systems. So it's not really difficult to prove this density version. So let us write proof. So I will not write the subscripts here. They are not very meaningful in this case. PZ1 is equal to, I can write this marginal density as the marginalization Rn2 of the joint distribution. Okay? PZ2 dZ2. Okay? So this is the marginalization formula, and I know that PZ1 given Z2 is nothing but the joint distribution Z1, Z2 divided by PZ2. Okay? This is the formula, conditioning formula. So the density function of Z1 given Z2 is a joint distribution divided by the marginal distribution of the conditioning variable. Okay? As a result, the joint distribution can be written as the multiplication of the conditional distribution times the marginal distribution of the conditioning variable. Okay? So instead of PZ1, Z2 here, I can write this condition distribution times PZ2. Okay? Rn2, and I can write here PZ1 given Z2, PZ2, dZ2. But this is nothing but this density version here. All right? So there is one thing here that I can mention, and it is nothing but the effect of extra conditionings. So sometimes we can have extra conditionings here. So Z1 given something else, and in that case I need to add those extra conditionings in all of the distributions here. So in the Chapman-Kolmogorov formula, you see that Y0k is in the conditioning. So here in this distribution, you can add these conditionings here, here, and here. And if you look at the density version of such, so let us write here extra conditionings. In this case, you can write the following formula. PZ1 given, I will here add an additional random vector Z3, okay? And I have here Z1 given Z3, then the total probability theorem just tells us that you need to add that conditioning here and here into these two distributions, and you're then fine. Okay, so I have Rn2 here, and I have PZ1 given Z2, and I will have the additional conditioning Z3 here. Okay, so here I have the same thing, Z1, Z2, Z3, and finally I have PZ2, add the additional conditioning here, Z3, and I have Z2 given Z3 dZ2. Okay? So this would give us the version of the total probability theorem once you have an additional conditioning. So when you go back to this formula here, you see that this is like Z1. This is like Z1, xk is like Z2, and Y0k is like the additional conditioning Z3 in this formula, okay? But this additional conditioning does not appear here, but it appears here. Why does it not appear here? It is actually, there is no harm here actually if you add Y0k here. Okay, so it is not harmful at all, but we are going to see in our course that when you try to look at the distribution of xk plus 1, when xk and Y0k is given, then you can remove Y0k here. It is only sufficient to keep here xk. So here you can add Y0k, but it doesn't have any effect. Such systems, this is similar to a property that is called Markov property, which we are going to see in our investigations in this course. Okay, so this is exactly the total probability theorem with extra conditioning, but after the extra conditioning, some of the variables might be erased from these conditionings if they are not necessary. Okay, so I will not prove this extra conditioning case. I will leave the proof as an exercise to you. It is again, the proof can be made again using these conditioning rules quite easily. So the next topic that I'm going to remind you is the so-called Bayes rule. Okay? Bayes rule is about replacing the conditioning with the argument of the distribution. So what is the relationship between Px given y and Py given x? So when I change the argument of the density with its conditioning, how those two quantities would be related. This is given, the answer is given by the so-called Bayes rule in probability. As I told you, Thomas Bayes is a very important statistician. I think he was British, English. And he represents, his approach to statistics represents one of the branches of the statistics. There are two branches of probability, frequentist approach and the Bayesian approach. Bayesian frequentist approach is represented by the statistician Fisher, and the Bayesian approach is represented by the work of Thomas Bayes. So the estimation methods like ML, maximum likelihood, or least squares, they are the approaches of the frequentist viewpoint, and they are really very important in the statistics. And the approaches like minimum mean square error or maximum a posteriori estimation, they are the Bayesian approaches. So these are two branches of statistics, and actually most of the time they don't agree with each other, and there is also always a competition between these two approaches. It's like a war or a fight, if you want to think about it like that. So Bayes rule is given also as a theorem here. So I would write it like this: Pz1 given Z2. So this is the density, this is the distribution version. It is not going to be much important, but the density version is probably more important. This is equal to, so I have Pz2 given Z1, I have Z2 given Z1, Pz1, these are capital P's, and I would have Pz2, okay? So this is the distribution version of the Bayes rule, or Bayes theorem, I can say. Now let us look at the density version. So the density version would be looking like this. So I have here P. These are now densities, not probabilities anymore. Z1 given Z1 given Z2 is equal to, I would have the density Z2 given Z1, and I would have here Z2 given Z1 divided by Pz1 divided by Pz2, the marginal distribution of Z2. Okay? So sometimes, not sometimes, in many times, we actually write this denominator in the following form. I take this, so Pz2 given Z2, this is, and I apply total probability theorem, the density version on it. Okay, so I have Rn1 here, and I write it Pz2 given Z1, PZ1, Z1, PZ1. Okay? So this is the total probability theorem applied on the denominator. So if I replace this denominator by this, then I'm going to get the following formula. PZ1, Z2, Z1, Z2 is equal to PZ2, Z1 and this is nothing but an integral of the numerator. Okay, so I have here Rn1 here, PZ2, Z1, Z2, Z1, and I have PZ1, Z1, DZ1 here. So here, this denominator is nothing but a normalization constant actually. So this conditional distribution is a proper distribution. So when I integrate this distribution with respect to Z1, the result should be 1. Okay? So this denominator is therefore nothing but a normalization constant for the numerator. So when I integrate this overall ratio with respect to Z1, the numerator and denominator would cancel each other and the result would be 1. So this numerator is nothing but a normalization constant. Constant with respect to Z1. Okay? So here I told you that this measurement update can be actually derived by this base rule here. So this denominator is nothing but a normalization constant actually for the numerator, to make this numerator a proper density, to convert it into a distribution function with respect to xk plus 1. So actually, in order to be able to do these probability calculations, you have to apply these two rules over and over for different conditionings. Actually, most of the times these are very mechanical rules that you can memorize, and when you work on estimation theory, these rules would become automatic, and they are tools that you can apply right away when you try to work on an estimation problem. So the base rule and total probability theorem are the main tools that you can derive some statistical estimation or Bayesian estimation algorithms to calculate the posterior distributions for the unknown variables. In the case of our system, these unknown variables are going to be the state variables, and the given variables would be the measurements for our case. So we would try to use these rules in order to be able to calculate the posterior density functions recursively. So just like the total probability theorem, the base rule can be, the density version can be proven quite easily. So I have P of Z1 given Z2 here. Here I will not write the subscripts. As you see, they don't carry much information here. So I will just write these distributions like this. I know that this is nothing but P of Z1, Z2 divided by P of Z2, but I can actually write P of Z1, Z2, sorry, this is, I can write P of Z2 given Z1 is nothing but P of Z1, Z2 divided by P of Z1, okay? Base rule is obtained by doing nothing but replacing this joint distribution here with the formula coming from the other one. I know that PZ1, Z2 is the multiplication of this distribution with this one. So this is equal to PZ2 given Z1 times PZ1. divided by pz2. Okay? So this is a basic proof of. So if you combine this part and this part, it would give you the base rule that I have written here. Okay? And just like the total probability theorem, we have an extra conditioning version of the base rule. So this was a proof. Extra conditioning. In that case, I will add an additional conditioning variable, Z3 here, okay? And the change that you have to do is nothing but add Z3 in all of the densities here. And that is the only thing that you have to change. So here, I will take that rule here, and I would add here Z1, Z2, Z3 here, Z1, Z2, Z3 is P of Z2 given Z1, but I will add Z3 everywhere, okay? So Z2 given Z1, Z3, and in the next density function, P of Z1 given Z3 again, Z1, Z3, divided by, in the denominator, I have P of Z2 given Z3, okay? So this is just a version of the base rule, and if you look at this measurement update, you can actually see that this yk plus 1, y0 to k plus 1 is nothing but y0k and yk plus 1, okay? So y0k is actually working like Z3 here. xk plus 1 is Z1, yk plus 1 is Z2 in those formulas, and y0k is like Z3. So here, y0k is here, y0k is here, y0k is not in this distribution, and that is going to be coming from the properties of the system that we will be working on. In general here, I can put here y0k, but it is not really necessary when xk plus 1 is given. Because of the properties of the measurement noise that we are going to assume, I will be able to remove this y0k from the conditioning given here. Okay? Really, you don't have to understand those type of things now. Now, the only thing that you should remember is this base rule. So here I have told you that this denominator is nothing but a normalization constant for this quantity to be a proper distribution function with respect to Z1, and actually I can write it as such. So Z1 given Z2, Z3, Z1, Z2, Z3, and this is, I will write everything in the numerator. Actually, I am quite bored of writing these conditionings. They are not, these subscripts, they are not serving any purpose here. But in order to give you some consistent notes, I continue writing them. So into this denominator, you can apply the total probability theorem with the extra conditioning, okay? And that is going to give you a normalization constant, and the normalization constant is going to be with respect to Z1 here. So I will repeat here everything: Z1, Z3, Z2, Z1, Z3, P Z1, Z3, Z1, sorry. Z3 dZ1, okay? So I have the extra conditioning version of the base rule given like this. And I won't prove this extra conditioning version of the base rule. I am leaving it to you as an exercise. It's not really difficult once you know the conditioning rules here. So the final thing that I'm going to cover in this last review lecture is going to be the function of random variables. This is really a topic that I cannot cover the whole of, because it's really an extensive topic. So I will just tell you that you might need to know such procedures in this course. Okay? So I will ask the following question. If you have a random variable xx such that it has a distribution pxx, suppose that I transform this random variable and I obtain the random variable y, then what would be the distribution pyy? Okay? Obviously here, this distribution is dependent on the distribution of x. So this distribution of y should come from the distribution of x, because of this relationship here. And how can you calculate the distribution of one random variable when it is a function of the other one? Okay? Here I will just solve a simple example, a very, very common example actually. And here, in order to not clutter the notation, I will just show the random variables with tildes. Okay? So suppose that the random variable x tilde is distributed px tilde x. The realization is shown as x, and the random variable itself is shown as x tilde. Okay? And suppose that y is equal to x squared. So this is my random variable definition. The random variable y tilde is the square of x tilde. And given this knowledge, what is py tilde y? Okay? So such calculations can be done, and there are some formulas in the literature. If you go back to your probability books, then you would see function of a single random variable, functions of multiple random variables, or we can have multiple functions of multiple random variables, etc. For each of them, you will have some formulas. And here, this is the simplest case. So we have a real valued function of a single random variable. Okay. So in general, this type of calculations can be done by calculating first the cumulative distribution function of the random variable y tilde. If I can calculate the cumulative distribution function of f of y tilde, then by taking the derivative of this cumulative distribution function with respect to y, then I would get this density function. Okay? So this is y is equal to probability of y tilde smaller than or equal to y. Okay? Then I will try to connect this with the distribution of the random variable x. So I have here, if y tilde is smaller than or equal to y, then I would have y tilde is x tilde square smaller than or equal to y. Okay? Now, depending on the value of y, this probability would change. Okay? If y is negative, then the square of a real variable can never be smaller than or equal to a negative number. That means that if y is negative, then fy tilde of y is equal to 0. Okay? Because this probability will be equal to 0 in that case. On the other hand, if y is larger than or equal to 0, I can write this probability x tilde square smaller than or equal to y as the following. So this is my function f of x. F of x is equal to x squared. Let us write f of x tilde is x tilde squared. This is x tilde, and this is y tilde. Okay? And if y tilde if y is actually non-negative, then y is somewhere here. Okay? And I'm looking at the possibility of x tilde square is smaller than y. So this is my y here, and I would have here square root y, and I would have here minus square root y. If x tilde square is smaller than y, then x tilde should be inside this interval. Okay? So this is therefore equal to, I'm continuing from here for positive y, for non-negative y values. This is equivalent to p of x tilde between square root y and minus square root y. Okay? And I can write this probability as follows. Probability of x tilde smaller than or equal to square root y, and minus probability of x tilde smaller than or equal to minus square root y. Okay? But this is nothing but the cumulative distribution function of x tilde when I substitute instead of x square root y. Okay? This is f of x tilde square root y minus f of x tilde minus square root y. So as a result, I have the cumulative distribution of y tilde is equal to this cumulative distribution of x tilde substituted by square root y minus the same thing substituted by minus square root y. So I have this expression. F of y tilde y is equal to f of x square root y and minus, this is x tilde, x tilde minus square root y. Okay? Then if I take the derivative of this cumulative distribution function on the left with respect to y, I would obtain the distribution function of y tilde. P of y tilde y is equal to derivative of this thing, derivative of this function is going to be the distribution of px tilde square root y times the derivative of the inside, 1 over 2 square root y here, okay? And minus, derivative of this thing is again px tilde minus square root y, and derivative of the inside is going to make this plus 1 over square root 2y. So if I take some parentheses here, py tilde y is equal to 1 over 2 square root y px tilde square root y plus px tilde minus square root y. Okay? So this is our final result. So you see that the distribution of square root y, y is given in terms of the distribution of the random variable x here. So now I'm going to finalize this review with the following example. So suppose that I have the random vector x. So let me remove the quantities here. So I have normal x, I have x bar and sigma x. Suppose that I have the random vector x distributed as a Gaussian and define the random variable y as ax. And A is a matrix here. Okay? And here I'm asking the distribution. What is the distribution that y has? So we're going to do this type of operations over and over in this course. Here, there is only one fact that you have to know. Fact. Linear transformations of jointly Gaussian random variables are also Gaussian distributed. Okay? So here, this x is definitely, all elements of x are jointly Gaussian distributed. And here, this is a linear transformation of the variables in x. All right? Therefore, y is going to be distributed as a Gaussian, with a Gaussian distribution. Okay? And as a result, I know that the distribution of y is going to be normal y, y bar, and sigma y. Okay? So the only thing that is remaining to us, so this is also again a function of a random vector. So we're asking a similar question here. And what I have to do here is to calculate only the mean of y and the covariance of y. Because I know the result is going to be a Gaussian distribution. So here, y is equal to a times x. So if I want to calculate the mean of y, it is going to be expected value of y here. But this is expected value a times x. So here expectation is a linear function, A is a linear function, so I can replace them. I always assume that the regularity conditions would hold to be able, for us to be able to make some replacements. So I have, this is A, EX, but this is nothing but X bar. So you see that the mean of Y should be A times the mean of X. And what about the covariance? In order to be able to calculate sigma y, I will first calculate y minus y bar. Y minus y bar is this one. Y is A times X, minus y bar is A times X bar. So this is A times X minus X bar. Okay? In order to be able to calculate the covariance of y, I need to calculate the outer product of this vector with itself. So y minus y bar transpose is equal to this vector A x minus x bar times this vector transposed. Transpose changes the order of the elements. X minus x bar transpose times A transpose. Okay? And then I'm going to take the expectation of both sides. If I take the expectation of this side, it's going to give me sigma y. And if I take the expectation of the right-hand side, A and A transpose can get outside the expectation, so I only have to take the expectation of this outer product. And it's going to be sigma x, the covariance of x. So this is A sigma x, A transpose. So now I have calculated the distribution of y. It is going to be a normal distribution in y, where the mean is A times the mean of x, and the variance, the covariance is A times covariance of x times A transpose. Okay? So you see that once you know the magical properties of a Gaussian distribution, obtaining the a linear function, density function of a linear function of a Gaussian random variable would be quite easy. You just have to, since a Gaussian is represented by only its mean and covariance, in order to be able to find the function of a Gaussian linear function of a Gaussian random variable, its density function, you only have to calculate the mean and the covariance of the resulting variable. And that would give you the whole distribution of the random variable or the random vector. So this completes actually my probability review. We are going to see if there are some new things that I missed here in this part. I'm going to remind you of those facts on the way. So in the next lecture, we are going to start with the actual topics of this course, which are going to be the state space models and the stochastic dynamical systems. That's all for this lecture. Thank you very much for watching.